Welcome to the day 4 of Masterclass 2022. It is organized by Women Plus in Geospatial, Regional Group Asia and Sub-Saharan Africa. So today we have very amazing topics. Topic 1, Precision Agriculture by Faith, and topic 2, Energy Access Explorer by Akansha. And I hope you all enjoy these topics. If you have any questions, please message us. We have day 3 questions open, so you can message us there and discuss. Thank you. Faith is a geospatial researcher with a background in GIS and remote sensing from Dayton Kemathi University of Technology. Currently an associate researcher at ICIPE. She has had her hands on various projects in agriculture while in KALRO. She has seemingly volunteered in various OpenStreetMap trainings and projects with Candid Training in Map Kibera Trust. Besides, she is certified in project management, leadership trainings, entrepreneurship, and public speaking from IBMI, mentorship, and beyond, and Talk General's Global Training School, respectively. Akansha is a GIS expert with energy program at WRI India. To visualize the energy access and development situation in Indian states, she is leading the creation of energy access maps that show the electrification data and overlays that with socio-economic conditions of the states. She has 5 years of experience in data analysis and geo-visualization. Akansha has worked extensively in health, finance, and governance project where she used geographical mapping and analysis to help and improve public delivery in health sector. Prior to joining WRI, she was working in 3D mapping of slums that involved rebuilding of slum area in smart cities with sustainable energy systems which allows for maximum use of the renewable energy. Akansha holds a master's in geoinformatics from Indian Institute of Remote Sensing, Indian Space Research Organization. She enjoys reading, traveling, and exploring new places.
Progress.
Hello, everyone. It's a wonderful morning, and I'm so glad and humbled to host this particular session. And today I'm honored to be talking about precision agriculture, the applications of GIS and AI in precision agriculture. And so the speaker today is Faith Ashono. I'm Faith Ashono. And Faith Ashono is a Kenyan lady who has a background in GIS and remote sensing from the Dedan Kimathi University of Technology. I'm a geospatial researcher currently, and I'm glad to be having my hands on some tasks, research tasks at ISIPE, International Center of Insect Physiology and Ecology. I've also been honored to have worked, to have worked in some projects in Cairo, the Kenya Agricultural and Livestock Organization. I've also been able to volunteer in various projects. I remember my first time during doing OpenStreetMap mapping was in Map Kibera Trust, where we had some tasks in mapping, especially in the Kibera region, and I also had my hands on some trainings and some tasks volunteering the OpenStreetMap. Also, apart from the GIS, it's also good for a person to grow, in particular in other fields. So I've been able to have going to school in project management, so I'm certified in project management, in leadership trainings, entrepreneurship, and public speaking from my BMI Mentorship and Beyond and General's Global Training School, respectively. And so today I'm honored to be speaking about precision agriculture. And so we go directly to our topic. Precision agriculture. Why precision agriculture? Actually, if we look at the current trends, all of us, we know what is happening. When we compare our time and the future as with the past, populations have really grown. There's an increase in population sizes, and actually, this whole population needs to eat because how can we exist without food? And the major challenge is that food amounts have increased because of the trends and the changes in climate change. And most farms don't produce actually a lot of produce because of tilling for a long time, because of the land losing its taste, the land losing its fertility. So yields have greatly reduced, and yet um, populations are increasing. So thanks to technology innovations and inventions that have come up so that we can be able to combat this particular tragedy that might be facing people. So the main issue here is to produce yields to feed the population, is to boost businesses, and precision agriculture has come in hand. So precision agriculture is the solution right now. People have to feed, people have to grow their businesses, people have to make money, people have to be innovative for the sake of the future. Because if we rely on whatever we've been working on, if we rely on the past technologies or the past activities, then we might not have much to produce. And now this precision agriculture has come. So how exactly and what exactly is precision agriculture? How is it being done? So according to research from the National Research Council 1997, precision agriculture is the application of modern information technologies to provide, to process, analyze multi-source data. So there's the use of modern information. Multi-source data means data from many sources of high spatial and temporal resolution. When we talk of spatial, it's in terms of location, and temporal is in terms of time for decision making and operations in the management of crop production. Crop production is just a whole topic, a wide topic that needs a careful analysis and the new technologies. So precision agriculture, the PA, is a new concept in agricultural methods. And the main aim of agriculture is to increase the yields or increase the production. It reduces the input cost because actually in farming you need to input for you to get the output. So what if the inputs are very high? Then it's going to be a loss to the farmer. So precision agriculture has come in to reduce the input cost, like the fertilizers output, application of pesticides, water, and again, it's helping manage and conserve the environment. In as much as we are farming, we need to conserve an environment because actually the environment right now is being choked, and we must do and put every necessary effort so that we can be able to conserve the environment. Because if we not take care of it, it's not going to take care of us, and vice versa. Well, so the advantages of using precision agriculture for the traditional methods. And there are differences between the two methods. For one is the focus. The traditional methods focus on the food needs of the farmer. Like a farmer goes to the farm just to get food for their family or their families, and it was done locally. However, there are those who want to an extent of planting crops for the sake of business that is making money. While precision agriculture, they produce food to meet the needs of increasing population. And like I said, our population is growing so fast. So precision agriculture helps to produce food in surplus. And also, apart from doing it locally, it's done in large scale. It's done in at large scale levels for profit. As much as it's producing food, it's also making profit. And then the techniques used in traditional methods, we like in spring, we had that hand sprayer. Of course, the farmer goes to the farm and sprays using that a small jerry can, the hand sprayer, cropping system, and the fertilizing, like you use the manure, the organic fertilizers from the cows, from the cow dung, the chicken, uh, the chicken waste, right? And then in precision agriculture right now, since it's large scale, then that means we have to really put in some effort, and that is when the drone sprayers come. It just does large scale within a short time and with high precision. We have the use of chemical fertilizers, like we have the NPKs and so on. In terms of labor, it was highly labor intensive, and precision agriculture is less labor intensive. You can imagine now that it's time to harvest, and you're trying to have people go do the harvest for you, like you're investing so much in labor. And sometimes even it could be an emergency, like there was a case when there was rain that is coming, and there were harvests from the farms. And when rain came, of course, it will destroy the whole harvest. So this person really had to do some task in making sure that people come forth so that they can be able to harvest that particular time before the rain comes. And you see, it's really labor intensive. Production, traditional method had low quality and low production, but with precision agriculture, we are assured of high quality and high production because right now, like in the traditional methods, you are sure like you're going to get some weird shapes. Like for instance, tomatoes, you'll find that there are those imperfect shapes, and there are those that they have their own shapes. But with position of purchase, you're assured of high quality, provided you put the necessary effort and you put everything in order. Then you expect high quality. You'll get high quality tomatoes, the perfect shape, carrots, no crooked carrots, and so on. So what technologies are being used to achieve this position and that we're talking about? We have GIS and remote sensing, we have artificial intelligence and smart apps. When we talk of GIS and remote sensing, we have like the drone sprayer, the drone, not sprayers I mean, but the drone satellites, they're like they pick information from up above, they pick information from the fields. We also have satellite imageries for that scale. And we also have artificial intelligence, like the models that are used to collect that particular information, assess the patterns in the data from the noisy data, of course, because it's multi-source, so we expect some errors and everything. So artificial intelligence uses models to collect this information, to clean it, to build models, learn the patterns, and maybe generate new data. And then the smart apps, they are the apps that have been generated or created and can be used on form for farmers to be able to monitor their fields with high precision. What are now the benefits of precision agriculture? Of course, it has a lot of benefits because you can be able to continuously monitor your crop, your soil optimal levels. Have the pH levels reduced? Have the pH levels increased? Has the moisture reduced? Has the moisture increased? And if they have reduced, what do I do? And if it's too much high, then what do I do? Real-time collection of data. The app enables you to collect information real-time. You can be able to know what's happening to your crops at that particular time. That's reduced the cost of production because you can be able to identify where you lack and where it's in excess. And so you apply input at those particular areas, unlike the traditional methods where we used to do it in large scale. And then also we are conserving the environment at the same time, right? So the next slide, onto the next slide. How specifically is AI being used to achieve precision farming? So one is crop and soil monitoring. Like with the AI, with ML models, ML meaning machine learning models, you can do the digital soil mapping. Digital soil mapping to monitor soil deficiencies like the pH, the nitrogen, phosphorus, and the potassium, the carbon content. We also have the micronutrients like zinc, copper, magnesium, and so on. We can be able to identify areas that have high amounts of these soils where there's deficiencies and advise appropriately. We also have the soil management zones where now we do the classification. We have another point is the disease diagnosis. We can be able to classify the disease and the diseases that are affecting particular plants, and we can strategize on how to eliminate them completely, eliminate the spread, and prevent them from reoccurring in these particular farms. The intelligence spraying, like I said, we now have the drone sprayers where they use the AI sensors to predict areas that have been affected by the weeds. And in turn, apply or spray pesticides in those particular fields. You can estimate the productivity and the quality of yields. For instance, now I've been able to know the input. I've been able to know the size of my farm. I've been able to know what I've planted. Then I can easily predict whatever amount I'm expecting at the time of harvest. And if I can predict the amount, I can also predict the quality. I can also predict the prices that are currently in the farm, the fluctuations, and I can be able to predict the maximum profit that I will get at the end of the harvest and that particular season in the market. Another thing is the climate patterns and generating predictive insights. GIS has come in handy because we have a lot of data. We can be able to understand the temperatures, the rainfall, the land uses, the land covers, and their changes over time using GIS and remote sensing. And AI-based robots have come in hand to help the farm harvesting because they've been able to tackle the labor challenge, and it's high precision. It provides a precision speed, and of course, it reduces wastage of crops because sometimes when you go as a person, you might tend to leave some crops in the field. That leads to wastage. But again, when you use robots, you can be able to pick everything in the field. And of course, since we said you can estimate the harvest that you will get, then you actually get the actual harvest you had intended to have. And so I want here to particularly talk about machine learning. So what's machine learning? Machine learning is a subset of AI. It focuses on getting machines to make decisions by feeding them data. This data is the data that we have collected in the fields using satellite imagery, using smartphones, using drone imagery, And so it makes sense from noisy data. Like I said, noisy data. Noisy data comes from the multi-source. It's raw data. So it learns the data. It tries to understand the patterns in the data. It makes sense out of the data. It derives insights. What could be leading to this? What could be causing this deficiency of a nutrient or whatever could be caused by what? And then it can generate insights, can generate new data from that. So machine learning is divided into three parts: the supervised learning, unsupervised learning, and reinforcement learning. So the main ones that are used, we have the supervised and unsupervised and like the reinforcement, because not many researchers have been able to apply this in their tasks. So what's supervised learning? I'm very sure we've heard about supervised learning in GIS. So supervised learning is like having a set of data. You feed that data. The data is generated by the user. So you feed that data to a function for prediction, right? And unsupervised, you have the data, and so the machine recognizes the patterns on itself to be able to predict the data. So like in imagery, I hope we've all done classification of images, whether Landsat images or Sentinel images. We've done image classification, like when you want to know the different types of land covers, like when you have the water, we have the forest, we have the agricultural area, the shrublands, the bare land, the urban. When we use supervised, we train the data set that we collect information, then we feed that information, that data to the image, and then we allow it to do the classification from our data that we've collected. So once you do your classification, you'll be able to identify the different land uses, land covers. And in unsupervised, now you don't provide any training data. So you have your image and then you specify the algorithm that you're going to use, you specify the number of classes that you're going to use, and then the machine itself now identifies the pattern and classifies the data. So it's the same case here in supervised learning. So the types of supervised learning have regression type, And under regression, we have the linear regression, multilinear regression. We have the nonlinear models like the decision tree and the random forest. We have classification types, um, like the KNN, the trees logistic regression, IS, SVM, which is a support vector machine. And in the unsupervised, mainly here we have them. The one that has been mostly used is the clustering. Clustering is grouping your data into a number of classes such that the ones that have similar characteristics are in one group and the ones that differ are separated, you know. There's the aggregation and segregation, like the ones with um, with with similar characteristics. It's aggregation and segregation, or segregation and aggregation. That is about the clustering. And so what outputs do we expect? What else outputs do we expect? Once we do our learning, we expect either continuous or categorical, where a continuous or categorical variables. For continuous variables, these are variables that have a value between minimum and maximum. So when you say like temperature, the minimum value was 2 and the maximum value was 20. So we have values from 2 to 20. So those are continuous variables. By categorical, they are fixed values or fixed numbers. Like we can say gender, it's either male or female. That's a categorical value. You can say height, either tall or short. That's a categorical value. So the machine learning process, you first of all have to identify the objective of the problem. What exactly do you want to solve? What exactly do you want to solve? Another thing is data collection. By the way, GIS, we identify that uh, sometimes we're given the data, like in forms of CSV or in forms of shapefile. And sometimes we have to collect the data ourselves, like the satellite imagery, download the images, and so on. And then now when you come here to data preparation, of course, we said we are collecting raw data. It's very noisy. So there are inconsistencies like missing values, duplicate values, or redundant variables. So we need to fix any of these inconsistencies. Fix any inconsistencies. After preparing the data, we have exploratory data analysis that we understand the trends and the patterns of this data. In here, we identify the count of this data, we identify the mean, the minimum, the maximum, the mean, the median, the mode. We identify the skewness, the kurtosis, how is data distributed. And here now we can be able to draw the useful insights, because once you do your data analysis, you can be able to identify the perfect model, might not really be perfect, but the best model, let me say the best model to apply into the data. You can also be able to understand correlations between variables. Like out of the many variables that are affecting the spatial distribution of a particular input, let's say, for instance, you're working on carbon content or you're working on pH. How are the other variables like the slope, the DM, every other thing affecting the distribution? And after that, you go to building the machine learning model. Now here I said you're choosing the right algorithm. If you're going to use a linear model, that is the linear regression. If you're going to use an nonlinear model, like the random forest. If you're doing classification, if you're doing support vector machine, if you're using supervised classification here, you have to split the data set into training and testing, because the training data is the one that you use to feed the model, and then the testing data is the one you're going to use to evaluate your model. Number 6 now is model evaluation and optimization. After fitting the model, you calculate the accuracy using the test data. How has the model performed? And if you think the model has not performed that really good, you can do parameter tuning to improve the model accuracy to reduce the time speed of the model running. And lastly, you can do the spatial prediction now here so that you can be able to generate the map. And as I said, once you do your predictions, you can be able to get the output that is either categorical and continuous. So this is the step that you follow when you're running any particular machine learning model. So here are some of outputs that I worked on at some time back. The first image is carbon content prediction using random forest in Borigusi catchment. So I follow those procedures and I use random forest, which is a nonlinear model. So random forest uses a number of trees to predict your data. So as you can see here, the output is a continuous variable because it has a minimum and a maximum value. You can see the yellow parts are the highest. We can see areas with yellow parts in the map. We have some pinkish that is in the middle. We have areas that are pinkish, and the lowest levels are the bluish, and the lowest levels are the dark blues. So you can see that the yellowish and the pinkish have high levels in order, and the bluish and the dark blue have the lowest levels. And so just to explain a little bit on this, we have, you see the areas with the yellow and the pinkish, these areas have very high carbon content. And from my study area map, this area is covered by forest. So I expect that areas with high forest to have high carbon content because these areas receive very high rainfall. These areas have low temperatures. These areas have a lot of leaves falling into the ground, from the leaves. So with high rainfall and low temperature, we expect decomposition to be so fast. And of course, with the leaves falling, that means there's a dense canopy and so on. There's a lot of carbon that is being preserved. And like the other areas where we have a little bit of low rainfall and high amount of temperature, there's high rate of decomposition of carbon. And so most of it is decomposed and easily washed away and of course there are a lot of trees in those areas, so there's no much content to help in manufacturing of the carbon. So my what I deduced from the study was actually true. Another thing, you also had me mention high rainfall or low temperature. Rainfall and temperature have very high correlation. They must be able to understand the correlation with some variables. Like where we have high rainfall, we expect low temperatures. Yeah. And onto the next map, I was doing clustering. Now this is the unsupervised classification. As you can see, my output from the region management zones, we have categorical variables that is fixed, like zone 1, zone 2, zone 3, and zone 4. So I was clustering the different macronutrients, the NPK and the pH, so that I can be able to identify the areas within the region, which areas have high level of pH, which areas have low level of carbon, and so on. So like zone 1, I was able to deduce like zone 1, zone 2, zone 3, and zone 4, all of them have different values of pH. They have fluctuating actually. Their values are not the same. So if we are to advise the farmers, we'll tell them, the farmers in zone 1, you're supposed to use a low amount of phosphorus, a low amount of phosphorus. And then I tell the people in zone 2, your pH is a bit acidic. You need to optimize, or you need to neutralize. So that is how we can be able to advise from these particular models. And so I will also just share some code from my R. From my R, machine learning models can be done either on R, on Python, depending on your preference. Yeah. Okay. So in R, here you can see I'm doing here is a multi-linear regression. So in R, first of all, you have to load the data set. I mean, to load the libraries, you run them because they're the ones that are going to help you perform the various tasks that you want to perform. And then once I load I have CSV, that is the soil data that is contained all the information. So that is the two, load the data set, identify the projection, load every other data set, like the slope, the DEM, or the bands from the Landsat image. I stack all these are the variables that help me predict this way. Like these variables can help me understand how does DEM influence the distribution of carbon and so on. And then I come, as I said, there's the exploratory data analysis so that here I can be able to understand the patterns and the trends that this data is following. So like identify the mean, identify the skewness, identify the characteristics. So I can be able to visualize this using histograms, box plots, the QQ plots, and so on. That is now in the exploratory data analysis. So after identifying the patterns, now I decide that here I'm going to use the model, the multilinear regression. So this is where from line 106, where I said the model fitting. Like I said, this is now the multilinear regression from line 118. So here I'm predicting carbon based on other aspects like bands, band 3, band 4, 5, curvature, BM land use, and VI, rainfall slope. You see, the topographic flatness index, and then I do the correlation, like I check of the various covariates or the environmental variables. How do they relate with one another and how they're going to affect the spatial distribution of carbon. After that, now I train my data set. I give an 80% training and 20% testing. So I'm going to use the 80% to predict my data set. So here I will learn 148. I'm predicting carbon using data that is the training data. And after that, now I am able to test the model validation. I test my data set, the model that I've made using the test data set that I split before. And I can test this using the RMSE, the R squared. R squared is usually in percentage. And also the MAE. After model validation, now I do the prediction. That is, I generate the map, the spatial prediction, so that I can be able to map. So the last line here, once I do the plot, that is, I get the map, the one that I've shared on my slides. That is multilinear regression. Here's another task that I done on random forest, the Murugusi catchment on the map. So load the libraries, load the data set, understand the trends of the data, clean the data that is removed any missing values, resampling and so on, so that we make sure that the data sets are in the same extent, exploratory data analysis using the histograms and so on to identify the patterns of the data. And so here I'm using the other covariates and environmental variables. So here I was doing, you see here the curve stack, I've stacked for the environmental variables. So I extract information, the soil, the soil data is in point form and the curve stack are in rasters. So I extract all this information into the soil, the point data, and then I run my random forest. Here I split the data set. I split it into 70 and 30. Also, the choice of the splitting data sets depends on what exactly you're running. So you can see I've split it into train and test data set. So I'm going to use the train data set. I'm going to use the train data set into doing my random forest. Once I do that, I do the model validation. That is, I identify the MAE, their squared, and so on. And then the last is the spatial prediction. That is mapping now after how is it spatially distributed. And after I do this, then now I get the map. And the last code that I want to show here now is the unsupervised classification, that is the clustering. So here I was clustering the main macronutrients, that is the NPK and also pH, so that I can go over to get the management zones. So the first thing is load the libraries, load the data sets, that is the point data is in form of CSV. And then now here, since I only had purely CSV, I had to get the rasters, that is the NPK. So what I did, I used random forest. Here is the exploratory data analysis. So I split my data into training and test. And then here, the next one, I used random forest to get the rasters for the nitrogen, the phosphorus, and the potassium, and also get the pH raster. And so here I did parameter tuning so that I can be able to increase the accuracy. And I used the grid search. In random forest, there are various ways of doing the parameter tuning. You can have the random search, you can have the grid search, and the manual search. So I did random forest for all the variables. Get nitrogen here, line 141, I was doing nitrogen. Line line 166 was doing phosphorus, and then line 187 was doing potassium, and line 43 I was doing pH. And then now I get the rasters. I now load the rasters I generated. This is potassium, nitrogen, phosphorus, and the pH. And then now I train my data, and then here I stack them, and then now I start my clustering. I use k-means, and I specify my clusters to be 4. So after that, now I'm able to get my output. I plotted, and that is how I came up with the soil management zone. So that is just to show the code, like what exactly is expected in what the processes in code. And you must really do a thorough research so that you can be able to understand all the processes, understand your codes, and also understand your output so that you can be able to advise accordingly. So I'll stop sharing my code at that point. I'm glad you're getting the insights. From there, I go to my slide. And so you can do the machine learning models in R, or you can do in Python, depending on whatever you are familiar with. For myself, I started learning R, although I'm also conversant with doing this in Python. And so actually, as technology is improving, you can use Google Earth Engine. You can do the machine learning in Google Earth Engine, because in Google Earth Engine, the data set is provided, especially for the Landsat imageries. And this data set, like, you do not really have to do the resampling and so on, unlike in R. So with Google Earth Engine, you can just use the data set as it is, because all the processes have been done for you. So that's it. And I'm so glad to teach about precision agriculture. Thank you so much for listening, and I hope you get insights. You're free to comment and ask any questions for clarification. So thank you so much. That comes to the end of my facilitation.
Hello everyone, I'm thrilled to be with you all here today to introduce the Energy Access Explorer for Jharkhand. This work would not be possible without the continuous support from a number of key data providers and partners. I cannot overemphasize the importance of energy access for socio-economic development and vice versa. Planning is essential to match the supply with the growing demand in the most cost effective way. In addition, energy planning is necessary if we are to move from centralized and expensive energy carriers towards fluctuating, decentralized, and cost effective renewable energy production. And to effectively expand energy access, we need data and analytical tools that capture key parameters of the unserved and the underserved. These key parameters are geospatial in nature. The gaps we have identified. Sorry. The gaps we have identified in existing ecosystem of geospatial analytical tools and platforms and multi-year stakeholder engagement exercise helped us better understand the requirement for the mapping platform we started conceptualizing and developing some years ago. The Energy Access Explorer. So the main three reasons and opportunities that guided us in the development of EAE are: first of all, there's a need to treat demand and supply as equal. If we do not understand demand from bottom up, supply strategies will not be viable, neither for the utilities nor for consumers, whether households or institutions. So we need a platform that synthesizes granular data on both demand and supply while taking into account other criteria and constraints which are geospatial in nature, such as location of health facilities, topography, and environment. Furthermore, it is essential to reduce reliance on GIS capacity and programming expertise. Planning agencies, clean energy enterprises, development financial institutions, healthcare departments with limited or no GIS capacity should be able to develop custom high resolution geospatial analysis on the fly. And the third reasons, uh, data providers and stakeholders, energy ministries, line ministries, REAs, need access to open source information system to reduce resource intensive software engineering cost. Note that the open source refers to no licensing cost, no subscription fees when it comes to the infrastructure. Data, however, can be either open source or password protected. So we designed Energy Access Explorer to be a modular tool that considers the dimensionality of energy access. Our vision is to provide geospatial data and technology and inform pathways to create a future where all people and institutions have access to affordable, reliable, and modern energy for achieving socio-economic development. So, what is EAE? EAE, it is an open source interactive platform that enables different stakeholders to identify areas where energy access can be expanded and linked to socioeconomic development. It synthesizes and analyzes several spatial data sets on both energy demand and supply. EAE can host different types of data at various resolutions, scales, and format. It uses data from open sensors, remote sensing, and satellite imageries, as well as national and subnational database. We should note that the data from other relevant geospatial initiatives can also be integrated into EAE. In the slides, you can see that we have shown demographic data, we have shown social and productive use data, we have shown infrastructure data, and we have shown energy resource data. And here are the main uses of EAE. EAE enables visualization of spatio-temporal data. It also allows strategic energy planning, where electrification planning agencies are able to link electrification and development. Service delivery institutions in the health, education, and livelihood centers will be able to estimate energy needs associated to development services. The tool has already been developed for Kenya, Tanzania, Uganda in close collaboration with key government agencies, and we have the tool for two states in India, and we are planning to expand it to more states. I would also like to talk a little bit about the backend of the platform. We have developed a customized content management system which allows administrators to add new data and metadata. We have automated data processing to minimize resource requirement when it comes to harmonizing, integrating, and updating existing one. We also have dynamic database and efficient data storage, variety of base maps including names of places, satellite imageries, and other, a modular API that connects backend of the application with the front end and enables users to generate rapid high resolution prioritization analysis on the fly. So EAE constitutes a dynamic geographical information system with an open source adaptable web architecture. Uh, Again, coming to the use of EAE, EAE allows you to use granular geospatial facility-wise data to track changes over time, prioritize intervention areas, and filter areas of interest. Yes. let me so this is the platform, this is a web page for EAE, and you can access it on www.energyaccessexplorer.org. So for India, when we talk about the data, we have divided the data in terms of uh, we have divided the data in health, education, demographics, and supply. So when we're talking about health, the data talks about the services that are there in the healthcare sector and the infrastructure in the healthcare sector. In the center panel, we can see the we have three tabs. We have tabs for data, we have tabs for filter area, and we have tabs for analysis. So if we talk about data in terms of services, we have done multiple stakeholder consultation with public health expert, and with the stakeholder consultation, we have come up with the different key performance indicators which are serviced at the district level, which are dependent on in the energy access. So let's take an example of institutional delivery. Institutional delivery, if we'll talk about, is the percentage of delivery that occurs in a public or private institutions. The platform has given the description in the metadata column, and it talks about the cautions which our users should follow, and what are the suggested citations you should give, and what is the source of the data set. We can see the source of the data set. So the platform allows user to actually track the data changes over the time. So right now we have the graph for 2012 13, and the and with the timeline, you can scroll the timeline and see how the changes are happening over the time period. And the platform also, this is when you're doing temporal change after one time period. But if you want to see how a particular district has say moved over the years, we can do that also. Let me go for Ranchi, which is the capital city of Jharkhand. And if we go, we can see that trend line which will tell how the particular district has been faring over time and space. So this is very effective if we want to track the changes over the time. The platform also allows the users to calculate the data, track more than one indicators, track more than two indicators, to see the dependency of indicators on the top of each other. So another feature of the platform is analysis. The platform allows you to do a multi-criteria analysis on the fly, and this is the most granular multi-criteria analysis which is present at the moment. So suppose suppose somebody wants to solarize health facilities. So what we have done, we have the location of the health facilities. The health facilities for Indian health system has been divided at district hospital, which is the highest level. Then we have community health center, which caters to somewhere between 80,000 to 100,000 population. So let's see if there is an initiative to solarize health facilities. With platform, the users can see what is the how is electricity coming there in a particular area. So we can see that electricity is coming. So we have a regular power cut, we have occasional power failure, we have a continuous power supply. So we let's focus on the facilities which have regular power cuts. So these are the facilities which are facing power cuts on regular basis, and according to the definition, it faces power cut at 4 to 8 hours depending on the facility. So if I want to solarize this, we know that global horizontal irradiance is very important, because it talks about the amount of solar sunlight which is coming in the ground, which can be used for your PV output and the efficiency of the system. So just overlaying the data on the top of each other will not give us a lot of inputs. But when we just move to analysis tab, we can see how the data has been changing over time and space. So we can see the distance, and then we have different kinds of potentials. We talk about energy access potential, which is like energy access potential is the combined aggregate of demand index and the supply index, because demand and supply has to come and talk to each other. Then we have assistance need index. Assistance need index comes into role when the facilities which are very poor or they need more assistance should be prioritized first. For today, let's focus on energy access potential. So we have just added it there. The literature says if you have GHI global horizontal irradiance more than 1800, it is very efficient. So let's change the value to 1800, and we'll see that we can prioritize the areas which has to be solarized. This also talks about the population share depending on the facilities. We can tweak it a little bit more, and we can focus on the areas where at the proximity of 5 kilometers for EAE. Let's put it at 12 kilometer. So it will also tell us the population share at particular area and the what is the where should it be prioritized, and this also allows you to identify the facilities which are at top 100 at its level. So this kind of analysis had been very useful, and we are also working with the different state renewable agencies, which allows which is using the platform on integrated energy planning, and how can the platform be useful to ensure that demand and supply are meeting each other and they're talking to each other. So let's talk a little bit more on about the platform and then we can close. So presently EAE, which is an integrated data driven approach for achieving universal access to energy, it covers around 32% of the total unserved and underserved population globally, which is a very huge number. Originally, this the platform was prototyped for 3 countries, but now it is there for more than 14 geographies, both at national level and subnational level. Then we have close partnership with more than 90 stakeholders and users. When we're talking about 90 stakeholders, these are government agencies, NGOs, different partners who are using the platform in their work and uh, trying to find out what is energy demand, energy supply, and how can they effectively use prioritize the interventions. We have more than 2000 returning users. So energy data info has also made its name in uh, the so energy access explorer is also a part of energy data info, which hosts all the energy access platform, energy related platform, which can, and then that is weighted by World Bank. So this I'll just stop here on EAE. I'll just stop here on EAE, and if you have any questions, feel free to please reach out to me on Akansha Saklani uh, at the rate of wri.org.
Thank you so much for joining us on day 4 of Masterclass 2022. Join us and grow your professional network. Register for our speaker database and show the world the amazing work you do. And put yourself out of your comfort zone from time to time. Get mentored and be a mentor and support the community. Speak up for yourself and the diversity and be the factor of change. Thank you so much. If you have any questions, you can message us in the comment section down below. Thank you.